In the figure below, block 1 has a mass of 460 grams, block 2 has a mass of 500 grams, and the pulley, which is mounted on a horizontal axle with negligible friction, has a radius of 5 centimeters. When released from rest, block 2 falls 75 centimeters in 5 seconds without the cord slipping on the pulley. What is the magnitude of the acceleration of the blocks? What are the tensions in the system? What is the magnitude of the pulley's angular acceleration? And what is its rotational inertia? In this system, we have two blocks, block 1 and block 2, that are hung from a pulley that has its own mass and its own moment of inertia. And when we release the system from rest, block 2 is heavier, so block 2 will go downwards, and block 1 will go upwards, and they will go at the same rate because they are connected by a rope. What's different about this case is that as block 2 goes downwards and block 1 goes upwards, the pulley will also begin to rotate, and it will have a angular velocity, but its angular velocity will be related to the velocities of the blocks based on the size of the pulley and the fact that the rope doesn't slip as the pulley rotates. So in this situation, the first thing we're asked is what is the magnitude of the acceleration of the blocks. We're told that block 2 falls by 7.5 centimeters in 5 seconds. So that is telling us a distance and a time. We know that the reason that block 2 is falling is because of gravity, and so what we're going to have here is a constant acceleration situation. Gravity is that constant acceleration. Due to the other masses in the system, block 2 won't be falling at the rate of gravity, but it will be falling with some proportion to the rate of gravity. And so we know that we can use our constant acceleration equations to solve for the acceleration of block 2. We need one other variable, however, and that one is hidden, is that we're told from rest, which tells us that V initial is equal to 0. With that information, we can find the acceleration due to gravity. We'll use the appropriate constant acceleration equation. We will eliminate this term because we know that we began at rest, and we can go ahead and plug in. We have 75 centimeters, so we want to convert that to meters, and our time is given in seconds. And we find that the acceleration is 0.06 meters per second squared. Now this is the acceleration of block 2 falling, but because they're connected by a rope, that's also the acceleration of block 1 going upwards. It's also proportional to the angular acceleration of the pulley, that the pulley initially was at rest. As block 2 falls and block 1 rises, the pulley will start spinning faster and faster clockwise, and thus it will have an angular acceleration, which we'll find shortly. First, we're asked about the tensions T1 and T2. We know that the tensions will act upward on the blocks, and in this situation, because they are acting on the pulley, we will see that these tensions end up being the torques that act on the pulley, because we'll have an equal and opposite reaction. This means that T1 will not equal T2. When we look at T2, we can find a free body diagram for M2. We know that we have the tension is upwards. We know that we have gravity downwards. And we know that our velocity and, as a result, our acceleration is downwards as well. So in this case, if we orient our axes downward, we'll see that the mass times acceleration is caused by gravity, and T2 is acting against that. If we rearrange terms, we see that T2 will be M2A minus, or M2G minus M2A, or T2 is in this case, M2 is our 500 grams, G is 9.8, and A is 0.06. And T2 is 4.875 newtons. We'll rewrite that as using our significant figures. We can do the same thing for T1. Looking at mass 1, we know that we have gravity acting downwards, and we know that we have T1 acting upwards, and for mass 1 we are moving upwards and we are accelerating upwards as well. So orienting our axes upward in this case to simplify our calculations, we see that M1A, the sum of the forces, is the tension minus gravity. Or we can see here tension is, we see that T1 is greater because T1 has to hold up M1 and accelerate it upward. It has to do both, and so its tension is a greater amount, relatively speaking. The mass of M1 is 460 grams, and we can find T1 thusly. Now that we want to find the magnitude of the pulley's angular acceleration, we know that the block 2 is falling at 0.06 meters per second squared. That block 2 is accelerating downward at that velocity. And we know that because it's connected by a rope, block 1 has to be accelerating upward with 0.06 meters per second squared of acceleration. So if the rope is going over the top of the pulley and down the other side without slipping, that means the outside edge of the pulley has to be accelerating at that rate as well. That has to be the tangential acceleration of the pulley as it rotates. If that's the case, we can relate the tangential acceleration of the pulley to its angular acceleration. In this case, we found the tangential acceleration. That is the constraint of the rope and the pulley. And we know that the radius of the pulley is 5 centimeters. And so we can find that the acceleration, the angular acceleration of the pulley must be 1.2 radians per second squared. Finally, we're asked about the rotational inertia of the pulley. We know that the pulley has some mass and it has some radius, and it's taking some effort to get it to rotate. We know how fast it's rotating. We know how much its angular acceleration is, and we want to find its moment of inertia, or its rotational inertia. The equation there then is that the sum of the torques is the rotational inertia multiplied by the angular acceleration. We know the angular acceleration, we don't know the torques, but we can look and we see what forces are acting on the pulley. We see that there is a torque, that the force T2 is acting at a distance from the axis of rotation, so T2 will create a torque. T1 is acting at a distance from the axis of rotation, so T1 will create a torque. If the pulley itself has a mass, that mass would be downwards, but that mass would be applied at the axis of rotation and thus would not create a torque. In this situation, we see that there should be a torque tau 1 that is T1 times the distance between T1 and the axis of rotation, which is the radius of the pulley. T1 is causing the pulley to rotate counterclockwise, so this should be a positive torque. And we see that the torque here should be .227 Newton meters. There should be a torque from tension 2. Tension 2 is also applied a distance r, the radius r of the pulley away from the axis of rotation, but tension 2 is causing the pulley to rotate clockwise, which is the negative direction. And so that has to be a negative torque. And we see that that torque is .244 Newton meters. Then the net torque will be the sum of these two torques, and we see that we have a net torque of negative 0.017 Newton meters. Now we know that the sum of our torques is the moment of inertia multiplied by the angular acceleration. We notice here as well, we know that the angular acceleration has a magnitude of 1.2, but the angular acceleration should also be negative because the angular acceleration is causing the pulley to rotate clockwise. And that solves our negative problem. And we find that the moment of inertia should be Now this doesn't, this seems like a small amount, but if we take into account the fact that the pulley is quite small, its radius is only 5 centimeters, we can look and we can calculate that its mass is about 11 kilograms, so it's quite heavy.